we'll solve this problem, which basically says that this little box called M in log letter is compressing a spring and then is released, and then it sticks together to a bigger box called M with capital letter, and then with the velocity of this one and this one together are attached to a pendulum, so they go up at a certain height. So we can divide this problem in 3 sections. First, solving this one before the collision with the conservation of energy, then with linear momentum in the second case, and the last one with conservation of energy. So for the first part, we know these values, the x, which is the distance between this wall and the mass, with a spring between them, and also the spring constant. So, and also we know that the surface is frictionless. So as I already said, this can be solved by the conservation of energy. The equation, it says that the initial kinetic energy and the initial potential energy is equal to the kinetic final energy plus the final potential energy plus Q, which means the work done by the friction force. But as it's said, it's a frictionless surface, then there is no Q. Well, we know that this means that 1/2 of the mass times the acceleration squared plus the potential energy, the elastic potential energy, 1/2 of the spring constant times the distance squared, plus mgh, the mass times the gravity times the height, equals to the final potential energy. It's the same equation, but with different values. For example, here the only energy done on the block is potential energy, since it's not moving, so this part can be removed. So, and the second part, when it's released, then there is no elastic energy, so we can take out the potential elastic energy. So this goes and this one stays. So basically what this means is that potential energy is transformed to kinetic energy. So 1/2 of the spring constant times the distance plus mgh equals 1/2 of the 1/2 of the mass times the velocity squared. And since there is existing mass, gravity, and height, we can put it. But here we don't have a height because it's at a low level. So also this part is cancelled, as well as this one. So 1/2 of the kinetic energy and this one, 1/2 of the potential energy, will be equal. So we know this variable, we know this variable, we know this variable. So here we can obtain the velocity of this block. So we only have to isolate a velocity. Here is the final result of the velocity. So with this one, we know the velocity of the M block of low letter for the next step. The next step is doing a linear momentum. So we know that the little block has already a velocity that will stick together to the big block. So here, with this velocity, we can get the linear momentum. We can say that the linear momentum is conserved or not. And linear momentum is defined by the equation P equals MUV. And then we can know that if the velocity is conserved, we can note it by when the both blocks are stick together again. So the equation will be like this: MB M equals M times B plus M capital R times B equals M UV. Also, but this comma means that is the final velocity that will be at the end of the collision. So and also we have to sum up M times B also times the final velocity. So since it's a frictionless surface, we know that the velocity will stay the same. Why? Because in a frictionless surface, the blocks will never stop and will move together along. So at the end, our equation will be something like this: mb times the initial velocity, m times the initial velocity equals m plus m times all that final velocity. So we only have to isolate the final velocity and we'll get an equation like this. Now we will move on to the final step. So we know that the conservation of energy formula is set by this equation. But since there is no air resistance and it's a frictionless surface and the blocks are already in there, we won't have any Q. So we'll erase it. And now these are the known values. We know that these blocks are already moving because we already had its velocity, so they have a kinetic energy. And then we'll end up at a certain height and they'll stop. So this means that they will have a potential energy. In the case, in the first case of this one, we went from potential energy to kinetic energy, and now we're going the other way around, from kinetic to potential. We have to remember that this velocity is the initial velocity from the other step, so we have to put a comma there, and we'll keep writing the equation. So we know that this is equal to the potential elastic energy of the spring, but since x means distance, but distance means distance done by a spring, so we don't have to put this on elastic energy. The only energy that we have to take into account is a potential gravitational energy. Also, we know that this m is the sum of the mass of the little block plus the mass of the big block. So our equation will be like this. And now we only have to isolate H. But for example, I always have many problems of what the problem was asking for at the first time. So I have this list of known values. So I check out which values I have and which I don't. So this one I have, this one I have, this one I have, and this one I have. So actually H is what we are looking for. So now we only have to isolate H. So this is how it would like our result.